Okay.
So you may just start when you're ready, please.
Thank you very much. Good morning, everybody. I'm Dr. Dimitrios Sklavakis. I have a bachelor in mathematics, almost 25 years experience of classroom teaching in secondary education, and literally thousands of hours of one-on-one tutoring in secondary and tertiary education. I have a master in artificial intelligence with expertise in expert systems and ontologies, and my PhD research was on using ontological engineering to develop authoring systems for intelligent tutoring systems in mathematics. And I'm going to present you my paper, Transforming Maple into an Intelligent Model Tracing Tutor. So, just a second. Here's an overview of the presentation. First, I'll make a short introduction to what model tracing tutors are, and then I will present the Maple model tracing algebra tutor that I have developed, and present its parts: the domain expertise model, the tutoring expertise model, the student model, the user interface. Then I will present two examples of a demonstration of the tutor, how the tutor behaves, some further work, and then we'll have time for questions and discussion. So, why model tracing tutors? Well, the history goes back to 1984 when Dr. Benjamin Bloom, an educational researcher, he discovered actually a method that would make a groundbreaking in education, raising student efficiency by 2 standard deviations. That means that the curve of the normal distribution of all students' performance could be shifted to the right by 2 standard deviations, 2 sigmas. What does this mean? That means that students taught by Bloom's method, 95% of them, that means 49 out of 50 students in Bloom's classroom would perform as good as the average student in a traditional classroom of 30 students taught with a traditional method. How did Bloom did it? Well, using 2 tools. First, mastery learning. Mastery learning means that each student must achieve true mastery of a topic, of a skill, before moving to the next one, more advanced. And the second one is one-on-one tutoring. That means that each student is assigned his own tutor, which guides him both inside exercises, solving exercises together, and guides him in the selection of the next exercises according to his mastery level. So he guides him through his whole education. So here you can see this is the normal distribution curve of a lecture, traditional classroom, and the blue one is the combination of Bloom's method with individual tutoring and mastery learning, which, as you can see here, it's shifted by 2 standard deviations. So why couldn't we implement and use Bloom's so successful system and revolutionize education? The reason was lack of resources, mainly time. For mastery learning, changing the traditional model of lectures to mastery learning, that means each student paces according to his capabilities and mastery of the domain, would require a total rearrangement of the educational design as we know it, and that means time for the teachers, extra time, and of course change of attitude. And the second one-on-one tutoring, that means that you need as many teachers as students, something that is practically impossible, more in our times where education is underfunded, as we know. So what did the problem? So the problem that still remains of implementing educational environments as effective as Bloom's it was called by Bloom as the 2 sigma problem. One solution proposed by the research community in education, and especially in artificial intelligence in education, was to develop digital tutors, since we have lack of human tutors, and they have built intelligent tutoring systems following the paradigm of expert systems. So intelligent tutoring systems didn't didn't achieve to perform as expected as the whole field of expert systems, but one particular kind of them, model tracing tutors, have been to be quite successful in STEM disciplines. That means mathematics, physics, and computer programming. The reason for their success is that they can approximate human tutor performance based on three expertise models that they are built with. The first is the domain expertise model or problem solver, and this model represents the knowledge that the students must acquire. And also this model is used by the tutor to produce the correct solutions, the correct steps in an exercise when it guides the student step by step. The second model was the pedagogical or tutoring model, which is the most important in such a tutor. This model performs two functions. The first one is it guides the student within an exercise, step by step, by taking the right solution steps from the problem solver, here, and comparing them to the student input. So it gives feedback whether the student input in each step is correct or not. In the same time, it builds the student model, which represents the mastery of the skills that the student must learn. And then, when it has built this student model, it uses this student model to perform mastery learning. According to the degree of mastery for each skill, the tutoring model decides which exercises or which topics to cover next. So I'm now going to present the Maple Model Tracing Algebra Tutor, which is as I have implemented it. The domain expertise model is 21 algebraic operations of expanding and factoring using Maple's expand and factor commands. These operations are 6 common algebraic operations like monomial multiplication, monomial power, monomial by polynomial multiplication, polynomial multiplication, elimination of parentheses, collection of like terms. 5 operations for expanding identities, square of sum and difference, cube of sum and difference, and product of sum by difference, which leads to difference of squares, and 10 factoring operations, common factor, factoring the expansion of a square of sum and difference, difference of squares, expansions of cubes of sum or difference, and sum or difference of cubes. And 2 methods for factoring trinomial. The first one is based on the sum and product of its roots, and the second one is the classical one using the roots of the trinomial using the quadratic formula. These are all so the tutor can teach step by step all these kind of operations and in combination, as I will show you in the demo. The tutoring model. The tutoring model is intelligent task recognition with deep model tracing. I'm going to explain it with an example now, using Maple's math container document tools, the inert form, op and ops commands. Why this? Let's consider this expression. It has 2 monomial by polynomial multiplications. And the first one, the student, let's say that expands the first product. The first partial multiplication is correct, denoted by the green color, and then the next 2 are wrong. The first one is, the correct is minus 15x squared, and the third one is plus 20x. So I have intendedly made 2 mistakes. So how does the tutor behave in this case? It parses these 2 expressions and creates an in representation and recognizes, here you see, I have used a nested list representation, which is actually a linear form of a tree representation, parsing the inner form using the op and ops commands of Maple. So here you see you have sum of 2 multiplications of monomial by polynomial, and here is the student input, 3 monomials, and the multiplication that he didn't perform. So what does the tutor do? It traces down deep to the smallest, to the elementary skill, which is monomial multiplication, the 3 partial products, and it gives feedback for each one of them. So this is actual tutor output to the student. You have performed a monomial polynomial multiplication, and for each partial product, the first one is correct. The second one, it's wrong, and it says that the exponent here, the exponent 1 of variable x is not correct. You must add the exponents of the variable. And the third one, the answer, this is wrong too. It says the coefficient minus 20 is not correct. You must multiply the coefficients of the monomials. Of course, we can adjust these feedback to be as fine-grained, as detailed we want. Finally, the student model. As I told you, the tutoring model, when it's doing this parsing, is building the student model. It's time-stamped, fine-grained, and skill mastery recording using record command of Maple. So, for the example I just have shown you, it creates 4 records. Each one has the student ID. Of course, the tutor doesn't do it now, but later it can solve it. It can save it to a database and call it back for mastery relating purposes. The session ID, which is the exercise that the student is doing, the date, the skill, it's multiply monomials with subskill all, and this is the first partial product which is correct. So this records that the first partial product was correct. And then comes the other 2. The multiply monomials, the subskill that he got wrong is add exponents. Here is the task, the answer, and it's not correct. The correct field is false. The third partial product, minus 5x times 4, the answer, it's false. The skill is multiply monomials, and the subskill is multiply coefficients. And the final one is for the overall operation, which was multiply monomial by polynomial, and the subskill was to multiply partially the monomials, and he got it wrong because he got 2 of the 3 partial products wrong. Yes?
Does it matter if he gets it in the wrong order? So if the 2 partial, if you permuted them all,
Yes?
what would happen?
You mean if the student gives the answer of the partial products in a different order?
Yeah.
I'll tell you what. For the moment, to keep things simple, I have made the assumption that he will multiply them in the order they see it. Otherwise, the parsing of the expression must be more complex, and you must find which is which is even difficult for a human tutor. I mean, if he performs both multiplications and he mixes the results, then it's even difficult for a tutor to, of course you can find it, but it needs more complex parsing, but it's possible. For the moment, I assume that he did it in the order that they appear on the polynomial. Thank you. So, this is the interface, as you can see it. I have a Maple math container for the initial expression that must be expanded. Subsequent math containers for student input for each step. For each step, there is an operation selection where the student selects what operation he will perform. And here is the tutor feedback for the student. This is for each step. They are repeated. These, as you will see in the demo, these document tool graphical user interfaces are repeated for each step of the solution of the exercise. And finally, on the top, here you can inspect the student model. Okay, now allow me to switch to Maple to give a demonstration of 2 examples, expanding this expression and factoring this one. Okay, this is the first example. I have already typed for time, to save time, the expression. This is the initial expression here. And here you have the first wrong answer of the student. I have made deliberately 2 mistakes, very common ones. The 2 is not correct, it should be 4, it's not raised to the second power. And the double product here should be 4xy. So let's see what I choose the expand tutor. Okay. So you see here it says, here's the output. You have performed a square of some difference expansion. It gives the terms. Term A is 2x, term B is minus y. And the square of term 2x is not correct. The coefficient 2 is not correct. You must raise the coefficient to the monomial to the exponent 2. And it continues. The double product is not correct. The coefficient minus 2 is not correct. You must multiply the coefficients of the monomials. So what does the student do? He must correct here 4, step back. Sorry. I didn't initialize the GUI, sorry. I'll do it again. Okay. Now that is correct.
But you're still missing a y squared?
Yes. Yes, exactly. I'll put now y squared plus. No, minus. It's minus. Okay, I'll step back. Excuse me?
Yeah, it's still bad.
Plus y squared.
Yes, it's still bad. Okay. Fine. So now everything is correct, and we can move to the next step. Okay. I will copy the expression, and now I'll perform this one, and I'll make another classical mistake. So 2 and 3 are not correct. They should be 4 and 9. And I get the feedback from the tutor here. You have performed a polynomial multiplication, and then you see that it finds the terms, and you see that it's a difference of squares. And it says the square of term is not correct. The coefficient 2 is not correct. You must raise the coefficient of the monomial to the exponent 2, and the same holds for 3y squared. It's not correct. The coefficient, you must raise the coefficient of the monomial to the exponent 2. So the student has to step back, correct the coefficients, and perform again the step. So now everything both are correct, and I can continue. I'll copy the expression. I'll eliminate this parenthesis, making a mistake. Oh, yes, here it's not correct, eh? Yes, the tutor found it, eh? I missed it, sorry. So it's better than me. Excuse me?
Makes for a convincing demo.
Yes, it is. So it finds mistakes that I miss. Okay, never mind. It's easy. It's easy. I'll step back, correct it, and retry. Now everything should be okay. Okay, and has the correct sign now. Thank you. Fine. So I'll make this mistake now. This minus is wrong. So I'll ask him to eliminate parentheses. You see it checks term by term for the signs, and here, where it finds the parentheses with the minus, it says that term minus 9y squared does not have the correct sign. And why is this? Because the sign of the parenthesis is minus 1, therefore the terms of the parenthesis must change their signs. So I have to step back, correct the mistake, redo the step. Let's see now. Okay, now it's correct. And final, excuse me. So what is the final operation? Collect like terms. These two must be eliminated, minus 4x and this one. And I'll make a final mistake. I'll omit my plus y squared. So let's see what feedback I'll get. It says here, okay, for the group of like terms, 4x squared minus 4x squared, your answer correctly omitted the reduced term since it is 0. For the group of like terms, minus 4xy, which is alone, it is correct. And for the final group, your answer is not correct. You must add the coefficients of the like terms. So I have to count back, turn 9 to 10, step back, perform again, and now everything is correct. And that concludes the exercise. Okay? And now you can see that during doing all these things, everything has been recorded in the student model. So here you can see all the steps with the skills and the sub-skills, and if they were correct or wrong. So you can recall them later and even see the mastery of a specific skill over time or over a specific period of time. So this can be used for mastery learning, to see where the student is in a detail down to each skill. Okay? Okay, we're fine. Second example. Okay, factoring this expression. I have made many mistakes in the first place. 2x is not correct. The common factor is 2x squared. And these are definitely not the partial quotients, but never mind. So the factor tutor says, analyzes the expression. I have intentionally leave the tutor being quite fluent, okay? I can control how fluent the tutor can be. So it's found the common factor is 2x squared, and the partial quotient is this one. And there's a factor by difference of squares in the next step. Your answer is not correct. Your common factor is not correct, says here. Okay, why is not correct? Because you must find the greatest common divisor of the coefficients and the smallest exponents of the common variables. So again, the same scenario goes on. I correct my answer. Oh, sorry. No, I did minus, it's minus 1. And this is not 32, it's 16. Okay, I step back, I recall the tutor. So it's correct, it says here, but it says that your quotient is correct, that is the quotient, but you can factor it further because the tutor recognizes that we have a difference of squares here. So the student must proceed, and the answer is, I'll get it correct this time, so I'll put here 4x squared plus 1 and times 4x squared minus 1. I'll get it correct just to proceed and save time. Okay, here is how the tutor analyzes. It's correct, and then I have another difference of squares where I'll make a mistake, and I'll put it like that. I'll put 4x minus 1 times 4x plus 1, which is wrong. It should be 2x, okay? And I'll call the tutor. Here it finds your answer says it's not correct. The terms are 2x and 1, the basis of the squares, and it says your term, what did the student answer? And it says your term A here is not correct. It must be the sum or difference of 2x and 1. That's for commutative situations. So I have to step back, turn the force to 2, call again the tutor, and everything is correct, and that concludes the solution of the exercise. Yes?
Can you change the 2x minus 1 to be 2 times x to the power 1 with an explicit power 1?
Here?
Yeah.
Okay. No, he doesn't.
So the middle one, though, it didn't, the first one, it said you can expand this further,
Yes.
but then the second step,
No, it didn't.
it didn't recognize.
No, it didn't recognize it. Yes. Usually because a common mistake is that after the common factor, they don't proceed. They don't look for identities. But yes, it's a. I think it's a. I didn't program it to do that. I programmed to just to recognize an identity immediately after the application of common factor, not until the end. Okay. Okay. Just to conclude. So further work planned. Of course, the challenge is to use this. As you can see, it's in development mode. It's quite experimental, and I would like to test it in real environments. I have already arranged with my school, the European School of Brussels III, where I work, to test it starting from November. Of course, a challenge is to extend it further to handle rational expressions, equations of first and second degree, inequalities of first and second degree, and rational equations and inequalities, but leading only to the previous two kinds. I mean, not equation equals more than second degree, okay? Because after the third degree, things change, and you have to use maybe Horn or other methods of factoring that go beyond the syllabus covered here. Thank you very much for your attention, and I will be glad to hear your questions and comments. Yes?
So suppose I was, well, like many of us are.
Excuse me?
Suppose, like many of us, we're difficult students.
Yes.
Suppose I hadn't seen, or hadn't chosen the common factor first. Suppose I had seen the 4x squared plus 1 as a factor of that
Yes.
original expression.
Yes.
Would you have been able to work with that?
Yes, because you may have seen commands for the partial methods of factoring, but these are for practicing isolated this skill. The factor tutor, as if you have seen, excuse me.
The student would have to tell the tutor what.
No, it calls the factor tutor. This is a command, and the tutor parses the whole expression and finds all kinds of possible factoring. So the student doesn't have to know to name the skill he's performing. The tutor recognizes it.
But the one before that they did, right?
No. It was only the first example.
Yeah, that's what.
Yes, the first example, the last two steps, only for collect like terms and eliminate parentheses. I have on purpose didn't put them in the expand tutor, and the student has to recognize them. But I can put them so the student calls always one command, expand tutor, and he recognizes that there are no. It's easy because if you parse such an expression, there are no other multiplications left or powers to expand. So it's easy to recognize that an expression has only left with parentheses. That means addition or subtraction of polynomials. And the same for collecting like terms.
And you could also have maybe done 2 steps at once.
Yes, the tutor also recognizes that. I don't have, I mean,
I believe you.
in the example I gave you, because you see here, no, I'll just show you the,
Yeah, I mean, I like what you're doing, but.
I mean here, if the student has expanded both multiplications, then you get here 6 monomials. So I can, the parser knows that there are no multiplications left, so you have expanded both. So it takes the first 3 for the first multiplication and the next 3 for the second one. Otherwise, it gets more complicated. You have to expand them and look each correct result, put it out, and keep what's left, but you don't know where does the error came from. Okay? It's one of the most difficult parts. When they get right, it's nice, but when they get it wrong, it's difficult to find what went wrong. And it definitely needs a lot of elaboration. Anything else?
Just curious.
Yes.
Do you have some record of the number of things that can go wrong or the number of things that you can detect? Right? Certain things can go wrong and in combinations.
Yes, you mean possible student errors?
Yeah, how deep is this tree? How many things can go
Very
wrong?
deep, very deep. I mean, you saw in the monomial multiplication, it checks everything that you would check as a teacher. Every possible mistake, coefficients, variables, leaving out terms, omitting variables, getting exponents wrong, but not everything. This will be repetitive process. It's just like you have to test the tutor because students are very resourceful in doing errors, and you cannot predict them all. And this is from my experience for 25 years of teaching in secondary education and one-to-one tutoring. Okay? But it's quite deep, believe me. You have seen the expansion of the identity. I checked each term, the double product, the coefficient of the double product, the variables, the exponents, everything. Otherwise, it's useless. Yes?
Are you using any of Maple behind the scenes to check that it's equivalent to the original expression?
Yes, of course. It's a Maple code. I mean, the parsing. How else? Yes, a lot of lines. So it's about 2,000 lines of Maple code. Yes?
So I know you said that you were going to be rolling it out to a class in November, but have you had a chance to force any of the students in your life to try it anyway?
Excuse me?
Have you had any students try this at all? If not in a class setting, but in your tutoring session or?
Not yet, but because I have been developing this.
Okay.
But in my PhD, I have developed another algebra tutor, which it was tested in my classrooms, but this was in 2010. But this tutor, no, it's not tested on any student yet. Anything else? Thank you very much.